Welcome to the Ephemeris podcast. I'm your host, Aphelion, and I think the only proper way to start this first episode is to introduce the podcast itself. So, the name, Ephemeris. I personally just chose it from a glossary of, astronomy terms, and if you just to look the definition up on Wikipedia, it is a book with tables that gives the trajectory of naturally occurring astronomical objects as well as artificial satellites in the sky, i.e., the position and possibly velocity over time. So I thought this kind of had a deeper meaning to creating a podcast because, it's kind of like creating a catalog of just really, really cool information on astronomy. And yeah, that's kind of what motivated me to do the whole podcast. So that's why I chose that title. As for the host name Aphelion, obviously it's a nom de guerre, right? It doesn't have too much meaning behind it. I just thought it was very suitable for the podcast. Having a little pseudonym. But if you wanted a meaning for that, I could just tell you Aphelion is kind of like if you were to imagine two celestial objects orbiting each other, kind of like a binary system. The Aphelion would be like the point in that orbit where the two celestial objects are the furthest. So yeah, that's the meaning of Aphelion. That's just going to be the name that I go by during the podcast because I think it just adds a little bit of something fresh to what we're doing here. And as for the photo in the in kind of like the cover art of the podcast, that is a personally produced image that I made of the Boomerang Nebula, and I thought it would be a lovely little logo to have there. And that's the heater going on. But yeah. So, without further ado, let's get into the topic of today's podcast, which, it's nothing too special, but I think it's still really, really intriguing. It's blue supergiants. So, I just kind of want to talk about, how amazing these things are when you really look into, how they form, where they exist, and, a bunch of other, quirky things about it. So, yeah, what are blue supergiants? So these things, if you were to imagine an HR diagram that kind of puts all of the different stars into perspective, right? You have the hottest stars towards the left and the biggest stars towards the top half of this diagram, right? Blue supergiants kind of belongs in that top left corner. So this is like an extreme of the kind of stars that can form in the universe. So everybody's pretty familiar with the stellar life cycle, right? You have two kind of stars that can form from stellar nurseries. There's a sun-like star, which is just going to become which is going to go through the main sequence and then become a red giant, and then kind of have a little planetary nebula moment before it becomes a white dwarf, right? And then you have massive stars, which will become red supergiants, and then they'll turn into supernova, and they'll either become a neutron star or a black hole or something of the sort, right? So you have extremes to that stellar life cycle, and blue supergiants is kind of on the extreme of the massive star side of it. So yeah, that's kind of why you'll see them belong in the top left corner of an HR diagram, as I've just explained. So in terms of actual numbers, these things can be 10,000 to 50,000 Kelvin, which is insane because if you put that into perspective, comparing it to the sun's just 5.4 thousand. So you're getting nearly tenfold. And the luminosity can be up to 1,000,000 times that of the sun, which is bonkers. I don't want to be anywhere near that. I'm happy to be away from those kind of stars, but they're magnificent. Yeah, if you're getting that kind of luminosity, you're gonna get an absolutely amazing star. So Compared to red supergiants, they tend to be like smaller in like radius, I think, or something like that. But they do have more mass than red supergiants. So so I mean, once you get that kind of information, you're like, I will not believe you until you tell me where these things exist and whether you can actually, prove to me that there are examples out there. So obviously, we're going to get into some of the cooler or more popular blue supergiants that can kind of put into perspective what these stars look like. So first, we've got Rigel. I'm going to call it Rigel. Perhaps it's Rigel. I do not know as of now, but that's something I'll maybe look into sometime else. But it is a blue supergiant star that exists in the constellation of Orion. So it's not, like, oh, it's billions of light years away that formed, early in the universe, because we'll get into why. We'll get into the complexity of the chemical composition too. But yeah, these things don't exist very far away from us. We've got so Rigel is about I'm trying to find the number 860 light years from the sun, which, I mean, if you put the universe in perspective, that's not very far. It's a spectral type B8 IA, or like Roman numeral 1A. So this thing's a B type star. It's not like the biggest and brightest that you can get, because if you look through a list of blue supergiant stars, you'll find, spectral class like O9.5, which is like way in the corner of that HR diagram, getting really bright. Or the composition being like extreme. In terms of having a lot of hydrogen and helium, which means it's like super massive. So some more about the star. It's about like 61.5 to around like 360,000 times as luminous as the sun. So again, not the most extreme, but just giving examples out there. It's about 18 to 24 times as massive as the sun, depending on the method and assumptions used. So yeah, that's one example. Then you've got UW, Canis Major, and actually quite a lot of the big ones exist in Canis Major. I believe Tau Canis Majoris is also up there with some of the craziest of the bunch. And so UW Canis Majoris is 07, so that's getting in on like extreme, and it's blue-white, obviously, because that's what O stars and B stars tend to be. So yeah, those are a couple of examples. I don't want to get too lengthy with examples, because we get it, right? They exist. So what's more interesting, though, is like the formation of these things, because I mean, I've mentioned before in this on this episode that the stellar life cycle is very familiar to us, but there are some aspects of the stellar life cycle when it comes to blue supergiants that we're not so sure about, and it gets kind of a little bit intriguing. So obviously, the first half of its stellar life cycle goes about as swimmingly as you would imagine. Except for the fact that it's usually a combination of two stars that forms, this huge giant ball of fire. So there will be two protostars. They'll come together. They'll become one star, and they'll do a whole lot of fusion. They'll have a lot of they'll intake a lot of hydrogen and turn it into a lot of helium, and that's also one reason why these stars actually do not last long, right? Because their fusion happens really, really quick. So yeah, as I said, lots of nuclear fusion, huge star, and then it like based on obviously the cycle of a massive star, it'll go into the becoming a supernova phase. So just looking at a couple of articles that I read about it before the podcast that I thought would give me a better understanding. So, as mentioned, supergiants will eventually die as supernova. They do still kind of have the option of they do still have the possibilities of becoming a neutron or a black hole. But I would like to think that considering how big these things get, surely they're going to turn into a supermassive black hole, right? But we're actually not, like, there are a couple of things when it comes to becoming a supernova phase as the star dies out that we're not quite sure about. So, coming from a space.com article, previous work suggested that when a star's core implodes, a burst of ghostly particles known as neutrinos carries much of the energy from this collapse outwards. Actually, no, wait. Yeah, okay, we're on the right. We're on the right portion. Oh, no, actually, you know what? Technical difficulties. Sorry about that. So, prior research could not explain how supernovas could occur from very massive blue supergiant stars with masses 50 times that of the Sun or more, even though astronomers have detected supernovas from these stars, right? So, prior research was like, yeah, sure, these things go as normally as a massive black hole would, but they kind of couldn't explain it because these things are huge. They're like genuinely not like the others. So they actually came up with this theory that as they can explode into supernovas, but instead of doing the whole neutrino thing, they create more exotic states of matter, right, from disintegrating protons and neutrons. Because this thing is a huge explosion. Supernova is a huge event in the cosmos. So, they called this exotic state of matter a quark-gluon plasma, which, I mean, you're obviously stepping into, the plasma territory, and there's so many different things that happens with plasma. It gets kind of crazy. There's a lot of physics research that goes into that. And the researchers suggested that this process of disintegration called quark deconfinement could generate, quote-unquote, a large amount of heat, resulting in a supernova, study-led author Tobias Fischer at the University of Wrocław in Poland told Space.com. So, yeah, I think that's even though you'd imagine it's a pretty like basic part of astronomy, kind of stars forming, I think once you get into the extremes of stars forming, you can get into some interesting territory where like a little bit of deep diving is involved. And so yeah, that's about all I have for you guys in today's episode about blue supergiants. Hopefully background noises obviously weren't too much of a disturbance. This first episode, I'm gonna get better at keeping things moving and a good flow of conversation. But this is kind of how we start out, and thank you for listening to the podcast. If you enjoyed what you heard, make sure to subscribe to the podcast on Spotify, and I will see you guys for another episode. Peace.